This video is about optical modeling. Probably you're already using COMSOL, CST Studio, Numerical or something else to find some scattering, some absorption, transmission or something. And probably you can compute all this stuff way much faster than you do now. And there is actually a package which is called TREAMS, and it uses not finite element technique but T matrices, and it can be especially useful if you want to compute many similar but slightly different problems. For example, you want to optimize stuff. And of course you may ask, I already use COMSOL, why should I even try something new, like contribute a lot of time, energy, and then understand that I probably don't even need this program, I probably don't even need this package. So this video is aimed exactly to help you to jump over this anti-barrier and to make you start with it way much easier. First, I will tell a little bit about what TREAMS is capable of, and then I will compute a couple of common examples, couple of useful examples, which you may then improve to and transform into the case you need. I'm also new to TREAMS. It's basically the first time I use it, so you need to understand my course can be not perfect, but I think it's probably better to do it like this and to be honest and to show how to start, because I'm also starting and it is actually not difficult at all. You only need to be capable of code a simple plot or polar plot in Python to be capable of using TREAMS. Of course, maybe with help of ChatGPT or something. Okay, let's make a short overview of what you can actually compute with TREAMS. And first of all, we have some incident wave, and it can be actually any type of wave: spherical, cylindrical, plane wave. Combinations you can probably use, but it cannot be that straightforward, but still possible. All of the following, which I'm going to tell after, can be done for isotropic materials. So anisotropic scatterers can be solved, but background medium should be isotropic. But it can be chiral. And the most basic problem TREAMS can do is, of course, scattering by a sphere of almost any size and material, probably not too big comparing to the wavelengths, but if it is too big, you can probably also not compute it with the COMSOL. You can find multipole decomposition, you can find fields and all the quantities, scattering, cross-section, absorption, and so on, but fields can only be calculated outside the particle. So if you need to compute fields inside the nanostructure, probably it is not that easy to do. The radiation patterns calculations of single scattering objects are unfortunately not built in, but if you know fields, of course you can compute radiation patterns just with little additional coding. So it can of course also calculate a multilayered sphere. It can calculate clusters of spheres and of multilayered spheres, clusters of spheres of different materials in reasonable time, probably up to 1000 particles if there are small particles. You can also download T-matrix from a T-matrix database for any possible object you will find in this database. Cylinders, cones, for example, are already there. Many other objects, you can find everything by the links in the description. Then you can compute any object of this shape if you will find it in database. But it is also important fields are still computed outside the circumscribing sphere of these objects. Infinite cylinders and of course clusters of infinite cylinders and multi-layered infinite cylinders, the same stuff as with spherical particles. It is built in, you don't need to go to the T-matrix database. Single particle on a substrate can unfortunately not be calculated, but you can actually use a life hack and calculate a periodic structure with a huge period, and absorption can help you with convergence. You can calculate a periodic array of particles and clusters mentioned above, so periodic arrays of clusters, and on any possible multilayered substrate. For periodic structures, transmission and reflection and so on, of course, it is built in. The band structure of one-dimensional periodic structures can also be calculated. There is option to choose different bases for multiple decomposition. There is very nice chelicity basis. You will see what is it and why is it cool. For example, in my another video about multiples, about vector spherical harmonics. So it is a cool basis from a symmetry point of view, let's say. Unfortunately, right now eigenmodes, so the nanoparticles cannot be calculated. It is not built in. One can still extract eigenmodes from what we have from in T matrices. I invite JD in comments to write a little more about it, but it's not straightforward. There is also a separate repository, GitHub repository for acoustics, which basically more or less the same functionality, so the same stuff scattered in, but in acoustical resonators. And there is also TREAMS, which is a differentiable version of T-matrix framework. And of course, you want to use it if you want to optimize particle positions and sizes. There is also TREAMS version for electric beams excitation, and all the links, of course, you will find in the description. And in the near future, functionality for calculating nonlinear processes can be added, so you can be probably also able to compute a second harmonic with this formalism. So to start, you basically need to understand physics of the processes as well as you need for COMSOL, and a little bit about how T matrices work, because it's essential to find some mistakes, for example, but I will explain it right now. That's all. A little bit of Python, because coding itself is now absolutely not difficult. Of course, if you know what you want and if you understand what you want. And of course, the most important knowledge is actually what T-matrix is. I will explain it for the case of nanostructure, some compact nanostructure, which can be placed inside some sphere, inside some surrounding sphere. T-matrix is associated with your object, with the sphere, with a nanostructure, with a cylinder, and it's different for different objects.
The T-matrix is a way to describe the response of an object to any possible incident field by knowing its responses to a set of basis functions. In the case of compact objects, these basis functions are vector spherical waves or multipoles. Any incident field can be written as a decomposition over this basis, with coefficients denoted here as A. In theory, the matrix is infinite, but numerically we keep only the first several terms up to some maximum multipolar order. Take, for example, a complex rotating electric dipole multipole, which is the first basis function. The first column of the T-matrix gives the coefficients in front of all outgoing multiples when the object is illuminated only by this incident dipole. The same is true for every other column and every other incident multiple. For a sphere, the T-matrix is diagonal. The incident electric dipole can only excite the corresponding outgoing electric dipole, and an incident magnetic dipole can only excite the same outgoing magnetic dipole. And for an arbitrary object, different multiples can couple to each other, so one incident multiple can excite many other outgoing multiples. So it's basically determined by symmetry. Once the T-matrix is known, we do not need to solve the full scattering problem again for every new illumination. We only decompose the incident field into multiples and multiply the coefficient vector by the T-matrix. That's all.
For spheres, cylinders, and periodic structures, it is basically built in TREAMS, but for any other objects, you can find it in T-matrix database. Of course, not for any other object, but if they are there, you can find them. Of course, the incident multiples have spherical Bessel functions as a radial part, but outgoing multiples, which are produced by T matrix after they have Hankel outgoing waves in radial part, and T matrix just connects them. Okay, and then I wanted to test TREAMS myself, so I just wrote a couple of codes, and of course, the first one is just scattering by a sphere. In my case, I used silicon sphere. And of course, to show like a little bit what is inside, I also built here scattering and absorption cross sections and multiple decompositions. And of course, I couldn't avoid trying to plot radiation pattern. And of course, I just used simple meteor to compare radiation pattern on this particular wavelengths. Radiation pattern is probably computed a little bit stupid, like you just compute fields far away, but it works. And how I did it, I actually asked ChatGPT to do it, and it provided me with the result immediately. Of course not. It actually made a few mistakes, which I didn't even notice until I was looking into the code, because it actually computed me like multipole and scattering response not under particular incidence, under particularly like linearly polarized plane wave, but averaged. But the problem was that the plots for average response in case of sphere and response under particular incidence are basically pretty much similar, so I actually needed to understand what's going on, because plane wave was not given initially, and this happened because there is an example with this average cross sections in TREAMS documentation, and ChatGPT just stole this example without understanding that I need actually something else. So if you write your very first code with TREAMS, please just check every block and what is done here and how is done and why is it done like this. You can ask also ChatGPT what it does step by step, what is done in this section, why it is done like this, why you're using this particular function, and so on and so on. It makes mistakes, but it is possible with that. Even if you are not able to code, you can write and compute and get a nice results. But okay, it is just a sphere and it was already mistaken, but then I just wanted to compute a dimer of two spheres, silicon and gold. And in this case, it is not meteor, it is not computed analytically. I have nothing to compare what to do if I want to compute dimer. Of course it is, TREAMS can do it, but how do you check if you do it correctly? So I found a paper, and just based on my previous code and based on this paper, I asked ChatGPT just to reproduce these results. Yes, how it is computed inside the TREAMS. It has a T matrix of single sphere, and it has T matrix of the second sphere, and then interaction and a common T matrix of these two spheres is computed, and it is actually not especially simple process. You need to decompose everything not in two different bases, because of course vector spherical harmonics, all of them are centered in the center of a sphere. So, and then you have two different spheres with two different centers. So you need actually to recompose vector spherical harmonics of one sphere and another sphere in one single basis, and you need to use some translation addition theorems. It's not simple what is happening inside, but after all, you just write a couple of lines in code and just get a common T matrix for these two, and you get your scattering cross section, absorption, whatever you want. And basically in this case, the graphs are similar, but they do not coincide with the paper I found perfectly. I could probably blame the dispersion of gold, because the paper says that they use Palic dispersion, but I couldn't even reproduce a single gold nanoparticle that it will be exactly the same as in paper. So it can probably be a problem, but probably the problem is something else. So I couldn't produce the results exactly, but they're still quite similar, which probably says that the code is not wrong. It's just different parameters are somehow used. And this was the second program I made. The third one is of course layered particle, but of course I just want to do something simple and what I can check with some papers, and it is silicon gold core shell sphere. And in this case, I have a perfect coincidence. Yes, in this case, there is also a coincidence for a single gold nanostructure, and it is probably the story of gold refractive index dependence, which I basically downloaded from refractive index info, and it is not the same in all possible papers. So yes, here for core shell we have a nice coincidence. And another example I checked, it was basically almost nothing I've done. I just gave ChatGPT all my previous codes, which for a single particle I checked properly, and then I just gave him parameters from the paper, gave him his previous correctly working codes, and okay, let's just reproduce this plots for a periodical array of silicon spheres. Works perfectly again. I can see the coincidence. I didn't check the coincidence point by point. It can be something like 10% difference maybe. But the point is that COMSOL results can also give you 10% difference between each other. I mean, finite element modeling is also not perfect, and experiment will of course be even worse because shapes are never perfect. So based on this, I can judge the code should work correctly, but do not trust it. I don't need these codes for my scientific work. I need these codes just to show you an example that TREAMS are not scary and can be used. Basically, even if you're not particularly good in coding, but if you want to compute something needed for your scientific work, please first compute it in two different ways, for example, finite elements method and TREAMS, compare it, and then you can slightly vary the parameters, and then probably be sure if you change something just a little bit, it will still be correct. And of course, check every line of your code. You need to at least to understand it, to know what it does. Don't rely on ChatGPT. Yes, it also made another mistake regarding the radiation pattern. Everything was absolutely wrong for a while. For example, spherical Bessel functions instead of spherical Hankel functions were used. Some stupid normalization constants were used, not constants. It was computed absolutely incorrectly for a while. It took me time to achieve a correct result, and it was not computed correctly even with the mean theory. It is easy to use now, but you also need to check everything. Of course, I will add all of these codes I show into the GitHub, but again, I don't need them to my scientific work. I couldn't contribute like 2 weeks of my time to make this video perfect, to make this codes perfect. It took me already several days, but I think it's still helpful. It's still helpful like this, and hopefully it helps you to actually find an energy and download the package and try it if you actually computing something of what I mentioned here, what TREAMS is capable of. Thank you for your attention.